Hey everyone, my name is Charlie Como, and this is my video lab report for our second lab. Our goal here is to computationally model the interaction of two charge tapes as a line charge, with the charges being uniformly distributed across its surface when the bottom tape begins to make the top one float. We will be reusing our data collected from Lab 1, where we assumed each tape to be a point charge and solved for the magnitude of the charge using fundamental electrophysics principles, then use Python to computationally approximate the sum of infinitesimally small point charges in the top tape, and lastly compare the two models' estimations for the tape's charge. For some background information, this is the electric force equation with its constants and characteristics shown on the screen. Note E is a fundamental physics constant. These are the derivations we will recycle from Lab 1, where as a point charge, the two tapes are in static equilibrium and the corresponding charge can be solved for like so. And these are some new derivations, which cover analytically calculating an electric field from an infinite amount of infinitesimally small, uniformly distributed point charge. Note the difference in the math complexity. But on the bright side, we will not be using this because we will be using Python to computationally approximate our charge like a Riemann sum, which will be much easier to do. Some simplifying assumptions we'll make are that we'll assume each tape has the same net charge and that this charge will be evenly distributed across the length of each tape. Note this is fundamentally different than assuming each tape as a point charge. Here are some videos of a confused physicist in action. Now here are two interacting U-tapes. I predicted that the two tapes will repel each other because of the same charge, and the video supported my beliefs with the split bottoms. Here's a charge check, which came back positive. It's ridiculous. Here's a gravity check of our U-tapes. I noticed that the top tapes began moving when the bottom tape was 2 centimeters away. Note, the length and width of all my tapes were 20 and 5 centimeters respectively, which led to a corresponding mass of 0.2 grams. Plugging in these experimentally measured numbers into our Lab 1 derivation yields a calculated charge of 9.33 times 10 to the negative 9th coulombs, and a gravitational and electric force magnitude of both 1.96 times 10 to the negative 3 newtons. Now we will input our experimental measurements into a Python model, which approximates each tape using 50 equal smaller components, calculate the net electric field at each top tape component due to all the bottom tape components, and we'll find that the computational model estimates a charge of 2.2146 times 10 to the negative 8th coulombs, with all the force arrows created as shown, and electric and gravitational forces equal in magnitude and opposite in direction. The white is the electric force, the yellow is gravitational, and the green arrows are the individual net electric fields of each tape component. Here's some analysis questions. I had previously discussed my answers for the first question, and for the second, I thought the differences in estimates were due to the single point charge model assuming the separation distance y is much greater than the length of the tape L, which allows L to disappear in its calculations, whereas the line charge model does not make that critical assumption and accounts for both variables in its calculations. Since the difference between y and L is just a factor of 10, that is not large enough to confidently make that assumption. Therefore, I believe that the line model charge is closer to the real value than that of the point charge. In conclusion, we successfully use fundamental physics principles and a line charge model to find the charge of each tape, which was 2.2146 times 10 to the negative 8th coulombs. If I were to do this again, one improvement could be to have more professional equipment to make better measurements instead of using my homemade ragtag gang of objects. Overall, this experiment was a success.